What's up, y'all? Yeah, turn this volume up. All right, today's Monday, April 13th. I was just looking at the schedule, and we have 5 class days left. Today and Wednesday, next Monday, next Wednesday, and then next Monday. And then that's the semester. And then what we would have done was taken the final that Friday. But we're going to have to do the final distance. So that will be just, like I think like these other tests have been, just a take-home test that you print off and send back to me. So what I want to do is finish up Chapter 6 today. So there's just the last section of Chapter 6, which deals with complex numbers. And then spend the rest of the time talking about Chapter 7. So we'll do the Chapter 6 test this week, and then we'll do the Chapter 7 test next week, or the Monday after that, and then the final exam that third week before Friday, which I believe is May 4th. What day is that? That would be May 1st. Friday, May 1st will be the last day. The deadline for the final, So yeah, that's the plan. Great. So Chapter 6 was all about radicals. You got pretty much everything down. How to simplify radicals using factoring, how to add and subtract radicals if they're the same. Whoops. How to multiply radicals. Hopefully you can, this is all the things that you should be able to do, and how to rationalize the denominator, aka divide radicals. And then a bunch of simplifying work, and then ultimately, how to solve equations involving radicals, and what to do while you're solving those equations, like having to check your work because of erroneous solutions. All that stuff was Chapter 6, and then we did a little bit on the Pythagorean theorem. So just in a nutshell, this is what we've been talking about, and hopefully what you're able to do at this point. The very last bit in Chapter 6 deals with a really cool topic called complex numbers. And it's necessary to kind of have complex numbers, at least be aware of them while you go into the next chapter, Chapter 7, because then you have to use them. So that's why I'm just going to throw this at you. They're really weird numbers. So here's the deal. If you tried to take the square root of -4, you come to kind of like a contradiction of sorts, because what this notation means is what number can you square to equal -4. And so what I usually like to do is tell people, like, when you say number, what number can you square to produce -4? That's where the problem lies, because at this point in algebra, you're probably looking for those numbers in between -infinity and infinity, which we call the real numbers. Capital R, because that's a title, not a description. Right? All numbers are real, in reality, exist in reality, but those numbers are titled the real numbers. And so that's why sometimes I like to call them the traditional numbers. So these are just, this is, if somebody asked you, you would say that's every number that exists. Right, but there is a way to kind of expand what you mean about numbers. There's to add more numbers into these so that this is possible. And here's what it looks like. You can say, all right, I do not know what the square root of -1 is, right? But we can imagine that it is a number and just give that a symbol, and you call that I. So let me just break that down. What you're doing here is you're saying, I am going to represent something using symbols because it's either impossible or very difficult to represent with the numerical system that we use, which is exactly the same idea as writing the square root of 2 just like that, rather than approximating it with a decimal. This is the only way to represent the number that you square to produce 2. You could approximate that number if you would like using decimals, or, but this is the perfect exact number. And it's the same idea here. The square root of -1, yeah, who knows? I mean, it's hard to make sense of that. But instead of that, let's just use the symbol. So that's a constant, right? I is a number, and that number is the number you would square to produce -1. Right? So it looks like this. I squared equals -1. So this is, I mean, it's just inherently confusing, I think, because the more you think about it, the more confusing it's probably going to be. And when I was learning this, they call this the imaginary unit, and they would call anything that involves I an imaginary number, right? And the realization that I had that really helped me was that that is not a description. That is just simply a title, and it's a bad title, honestly, because it gives people the impression that they don't exist, and that they are purely in our heads. And that's not true. This is a number just like any other number. It's not a traditional number. It's, so what I would do if I were you is just not think too hard about it. Just, you know what I mean? Just be like, all right, hey, can you square something to get -1? Yes. What number? I. What's I? It's the square root of -1. How's that possible? Move past it. You know what I mean? That's how I would do it. So yeah, this is fundamental, right? And these are two things that you should definitely have memorized. So this is the basis of complex numbers. And let me just say again, if you're reading about this on the internet or in the textbook, they'll probably call these imaginary numbers, and they would call these real numbers. But I really like to get away from that language because it's not informative. It's not telling you that those are real and these aren't. They're just titles that are, in my opinion, misleading, right? It's like if your last name was Thief. Like you're not, or if your last name is Baker, you don't have to be a baker. You know what I mean? It's just your last name. So that's what it is. That's why I call them the complex numbers. I call these the traditional numbers. Right, so what can you do now? This is the type of thing you can do once you've accepted this. Take the square root of, say, -4. Right? And now this works exactly like it does in Chapter 6 with traditional numbers. Here's how I would simplify this. You can rewrite -4 as -1 times 4. Then you can use that property of exponents that we've been using the whole time to split this up into the square root of -1 times the square root of 4. The square root of -1 is the number I, and the square root of 4 is the number 2. So you get I times 2, which we normally write as 2I. You treat it like a variable, but it's not a variable. It's a constant. It's the square root of -1. So the square root of 4 is 2I. So look, let me make another point here, that when I say the square root of -4 is 2I, or really whenever you see the number I, it's just kind of a flag. It's a symbolic flag that says somewhere under a square root sign there was a negative. And rather than using this kind of cumbersome notation, we go and use I instead of square roots of negative numbers. So you'll never see square roots of negatives because the notation for that is I. All right, so here's another example. Take the square root of -24. And you can simplify this. I mean, you would just have a question that says, hey, look, simplify this square root. And you would do it the exact same way that we have been doing it. You can rewrite -24 as -1 times 4 times 6. can split this up using the property of radicals. Square root of -1 multiplied by the square root of 4 multiplied by the square root of 6. The square root of -1 is the number I. The square root of 4 is the number 2. And the square root of 6, there's nothing you can do with that, so you leave it alone. I times 2 times root 6 should be written this way. 2I root 6. Right, so it's three things being multiplied together, but this is how you're going to see it written out. So it's really similar. It's really similar, and in fact, honestly, this is what I do when I am simplifying square roots with negatives. If I have a negative under a square root, I will just remove the negative sign and put an I on the outside. So, remember what we were saying? If you have the square root of, say, 50, and you rewrite that as 25 times 2, and then you can take the 25 out as a 5. That's what I do with a negative sign. I take a negative out as an I. And that's because a negative sign is the number -1, and the square root of -1 is the number I. Okay, so, honestly, I think most of the problem that I've seen with people with complex numbers is kind of like philosophical rather than calculatory, because the calculations are the same you've been doing. And so I would focus on that if I were you. And if you really are interested in you super want to dive into complex numbers and kind of like the reasoning behind it, you should for sure. But as far as what you're going to need to be able to do in Math 105 and even Math 151 is simplifying negative square roots, just like this. So that's what I would focus on, practically speaking, if I were you. Great. All right, here, let me have you try one then. So yeah, you should definitely make an effort to memorize the fact that I is the square root of -1 and I squared is -1. But reference that if you need until then. So let's say simplify something like this. Square root of -75. Try that. Also try to simplify the negative square root of -8. So simplify both of those. Pause the video if you'd like to give it a go. Here's how I would do this. Technically speaking, you should rewrite -75 as -1 multiplied by 75. Now you can use the property of exponents to say the property of radicals to say that's the square root of -1 multiplied by the square root of 75, which is I root 75, because the square root of -1 is I. It just turns into I. All right, so that's like the process. But truthfully, this is what I was saying I do. If I have a negative under a square root, I just remove it as an I. Now, just treat this like you would have any other problem. Square root of 75, and just keep the I out front. 75 is 25 times 3. The 25 comes out as a 5 and multiplies. So you get 5I root 3. You should compare that to just the square root of 75. Simplify just the square root of 75. Well, you get 25 times 3. The 25 comes out as a 5, and you get 5 root 3. So this is what I was saying. The I is simply a flag. It's just saying all I is saying is, hey, what was under that was negative. So it's the same exact answer other than the I. And all the I is telling you is that you took a square root of a -1. Great. Negative square root of -8. So yeah, I would just run the process like normal. This should be negative square root -1 times 8. So the -1 comes out as an I. The square root of -1 is I. So that becomes -I, which is possible. negative I would be the negative square root of negative 1. Right, so here's a thing that can get confusing too, is that the square root of negative 1 isn't a positive or negative number. It's not, complex numbers aren't positive or negative, so that's could be very confusing. You can make it, you can multiply it by negative 1. So what I'm saying is that when you pull out an I, don't make the mistake of canceling a negative. That doesn't work with complex numbers. But you can multiply it by the negative. So really this is just negative 1 multiplied by I, which we write as negative I. So negative I root 8. Now you simplify the square root of 8, make it 4 times 2. The 4 comes out as a 2. So this should be negative 2I root 2. Cool. All right, yeah, so get some good practice with that, and really that's all you're going to need to be able to do what's necessary in the next chapter. The next chapter has a lot to do, so we're going to be using some calculations where the square root's going to come up a lot, and sometimes under that square root, a negative will appear. And what, now that we've talked about this, you have the capability of simplifying that rather than having to be like, oh, undefined, can't do it. Now you can do it. So we'll get to that. I'll put a bunch of these in the homework, and that'll be that. By the way, there's just so much more with complex numbers. Obviously, that is just literally step 1. We're just running out of time, and it's really too bad that things have to get sacrificed. So, might be worth a read through the chapter. I think that was 6.6. 6.6 is the complex chapter. Let me just verify that. 6.8 is the complex numbers chapter. So it's probably worth a read through if you're continuing on to college algebra. But you'll get that practice when you take that class. So cool. Well, that's chapter 6. Chapter 6 is done. That's all I want to talk about. Chapter 6. So I'll put the test on the test tab in Blackboard. Same deal. Just print the test, take it, email me scans of it. I'll put the due dates on Blackboard when I post it. I'm thinking a week from today. So due next Monday. Cool. All right, then let's just hop into chapter 7 and talk about the first bit. So I just want to talk about the first section of chapter 7 and kind of introduce the chapter and what it's all about. So chapter 7 is all about quadratic equations. We've already talked about quadratic equations. They're a type of polynomial equation. It's a second degree polynomial equation. It's not necessarily a trinomial. So here is what a quadratic equation is. This is the generalized form. Looks like this. Something x squared plus something times x plus something equals 0. So this A, B, and C deal is really just saying those numbers can be anything. Make A anything, make B anything, make C anything. If it looks like that, it's a quadratic equation. For example, 3x squared plus 2x plus 1 equals 0 is a quadratic equation. 4x squared plus 2 equals 0 is a quadratic equation. Notice that there is no bx here, but I could have, if I wanted to, written that as 4x squared plus 0x plus 2 equals 0. And now it does look exactly the same. The only thing is that when you have 0 times x, we don't normally write that. But you could explicitly write it in if you wanted it to fit the form. So this form is every quadratic that you could possibly imagine. Every single quadratic equation can be made to look like this. If it doesn't look like that, you can do some algebra to make it look like that. You know, for example, let's say you had something like negative 3x equals 4 plus 2x squared. Right, so this does not look like this, but I can, if I wanted to, go like this, add 3x to both sides. Negative 3x plus 3x is 0. And then I could rearrange this and write it in descending order. So I'll write the 2x squared first, I'll write the plus 3x second, and I'll write the plus 4 third. Boom. So that's called putting a quadratic in standard form. The thing about standard form that is nice is these three numbers, a, b, and c, are going to be super powerful for solving quadratics. Right, so that's what a quadratic is. Honestly, it's just something that looks like this, or can be made to look like this. So if you have a quadratic, how do you solve it? That's what the topic of the chapter is. Well, we've already talked about this a bit. You know, like let's say you had a quadratic like x squared plus like x squared minus 4 equals 0. Right, so this is a quadratic. A good thing to do when you're solving quadratics is to identify a, b, and c straight away. So if you were asked to take the quadratic and identify a, b, and c from the standard form, you would say, all right, well, a in this case is 1. A is the thing being multiplied by x squared. So a is 1 in this case. B is the thing being multiplied by x. There is no x here, which means it's 0. And c is just the additional number, which in this case is negative 4. It always has to be equal to 0 to fit the form, right? So if this had said something like this, now a, b, and c aren't those numbers anymore. In order for you to identify a, b, and c, you have to have it written in standard form, which is everything on one side in descending order and 0 on the other side. So the first thing you would have to do to put this in standard form is minus 2 from both sides. X squared equals x squared minus 6 equals 0. Now you can identify a is 1, b is 0, and c is negative 6. Great. Yeah, so identifying a, b, and c is a good starting point. But in the end of chapter 4, we talked about how to solve quadratics using factoring, which I think is an awesome way to solve quadratics. So you put everything to one side in descending order, 0 on the other side, and then you factor. This is a difference of squares, so you get plus 2 minus 2. Once you've factored something, you have two things multiplied together equals 0, which you could use the zero factor property to say, well, then one of those things must be 0. Now you've split this into two linear equations, which you can easily solve by isolating the variable. Right, so x equals 2 or x equals negative 2. There's two answers, as there always will be, to quadratics. Two answers, 2 or negative 2, will make this a true statement. Awesome. Yeah, so factoring is a great strategy for solving quadratics. I really like solving quadratics using factoring because the logic is just really, it works out nice. You get to practice factoring. It's one of my favorite ways to solve them. The problem is that not every quadratic can be solved using factoring because not every polynomial can be factored. That doesn't mean that you can't solve the quadratic, that just means you can't use factoring as that strategy. For example, x squared minus 5 equals 0. So there's a bit of some subtlety here because once you get like advanced factoring, you can factor anything almost. So you technically could factor this, but the way that we've been talking about factoring is using whole numbers. So you're not going to be able to do that the way that we've been talking about it. Because if you try to, you're looking for, you got x squared because x and x because it's x squared. But now you're looking for two numbers that multiply to negative 5 that add to 0. And you're not going to find anything using the whole numbers. So, that's not factorable the way that we've been talking about factoring. Okay, so that happens sometimes. Sometimes you can't factor quadratics. Well, there's a bunch of other strategies on how to solve quadratics. And that's what we're going to talk about. So there's like 3 other strategies that you could use to solve quadratics. One of them that's really nice is this thing where you just take the square root of both sides. So I like to call it the square root trick. But, there's a special condition that has to be met if you're to use the square root trick. And it is that b has to be 0. Right? So you need to not have a bx term, which means that b was 0. When that's the case, then you can do this. Add 5 to both sides. X squared equals 5. And then just take the square root of both sides. Right, so square rooting cancels a square. So you get x equals the square root of 5. So I was saying there's always 2 answers to quadratics. That's only one answer. So where's the other one? Well, in chapter 6, we did a little band-aid thing that said when you take the square root of x squared, you just get x if x is only positive numbers. If it's not, the square root of x squared is the absolute value of x. So this is going to come back now, because that's what's happening here. When you take the square root of x squared in order to solve this, you actually get the absolute value of x equals, well, the square root of x squared is the absolute value of x. And now, if you remember how to solve absolute value equations from chapter 1, you say if the absolute value of x equals square root of 5, then x equals positive that, or x equals negative that. So yeah, there's a lot of stuff to kind of like recall and come back to. There's 2 answers now, square root of 5 or the negative square root of 5. You should check both of those, and you should prove to yourself that those both are solutions to this original equation. Right? You're asking yourself, what squared minus 5 is equal to 0? And you found the square root of 5 was one of those answers. Square root of 5 squared is 5, and 5 minus 5 is 0. So the square root of 5 works. Great. The negative square root of 5 squared is negative root 5 times negative root 5, which is positive 5. 5 minus 5 is 0. So they both work. Those are 2 solutions to this quadratic, as there always will be. 2 solutions. Yeah, so what a lot of people do is, if you have something like this, say, you can always take the square root of both sides of an equation. But you just have to remember that when you take the square root, you actually have 2 things that you need to consider. So what I like to do is just run it, logically exactly. The square root of x squared is the absolute value of x. And then the square root of 4, you can write as 2. And now this is an absolute value equation. And absolute value equations have 2 answers because there's 2 ways that you can go from 0. Absolute value of x equals 2 means x equals 2 or x equals negative 2. Okay, but I should tell you that some people do this kind of different notation where you can take this, so, x squared equals 4, and you could take the square root of both sides. And then they say this, x equals plus or minus 2. And they write it out in one line like that. So that's fine. You should just know that this is a shorthand for two things. X is 2 or x is negative 2. I like to be super explicit when I write things. This notation is common, so you should be aware of it, but if it were me, I would be like, it's this one or this one. Because I just feel like this gives you the impression that it's, and it's very easy to kind of like forget one of them and just say x is equal to 2. You know, but it's not. It's both plus and minus 2. Writing it out in one line could be confusing. I'm not saying I'm not okay with this. Feel free to do it, right? But just know and hopefully be clear that that is two things. So when you take the square root of both sides of an equation, you need to account for both the positive and the negative versions. And that's because when you cancel a square with a square root, the absolute value results. Cool. All right, so here, give a couple a try. Try x squared equals 7. And try 2x squared plus 4 equals 0. Yeah, so pause the video if you'd like to try both of those. So solve the following quadratics. That's what you would see as directions. When I am solving quadratic equations, I really, there's a process that you should go through. Both of these quadratics are missing their b term. There is no bx term here, just an x squared term and a number. And when that's the case, you can use the square root. So that's what I would do on both of these. To use the square root, you move the numbers to one side, and then you use the square root to cancel the square. It's on you to remember that when you do that, you have to account for both the positive and the negative versions of your resulting, of the other side. So it's either the square root of 7 or the negative square root of 7. One way that you can really remember that is by always writing the square root of x squared as the absolute value of x, and then just continuing to solve the absolute value equation after you've done that. So that'd be a good way to remember if you find yourself forgetting a lot. Do something like this, and then say, okay, well then that means that x equals root 7, or x equals negative root 7. Just there's two answers every time. A quadratic will have two answers, bottom line. So if you're only getting one, there's a problem. All right, this one here, you should watch out for, there's some other tricks of the trade here. First of all, this is a quadratic. It's missing the b term, so I would use the square root trick. To do that, you should minus 4 from both sides. Write it as 2x squared equals negative 4. And now you can divide by 2 on both sides and write it as x squared equals negative 2. Right, so if you didn't do that, when you took the square root, you'd be taking the square root of 2x squared rather than just x squared, which is doable. You could totally do that. It will make it a bit more complicated to cancel the square. So that's how I would handle that. Now, take the square root of both sides. The square root of x squared is the absolute value of x, and the square root of negative 2 is I root 2. Ha! It's coming back. This is why you need to know about I. It's because when you go to solve quadratics, square root comes up a lot. Under that square root, negatives appear a lot. So you can simplify them now. So now you can continue to solve those quadratics without having to stop. All right, so if the absolute value of x equals blank, that means x equals positive blank or x equals negative blank. That's how I like to think about that. I mean, that's why you're getting two answers when you solve quadratics. There's this I mean, sometimes, because there's this absolute value thing happening. So positive blah or negative blah. Without doing that, you don't have to do that absolute value thing. Some people just say, look, I'm taking the square root of both sides, which means x equals plus or minus blah. And that's totally cool. It's totally cool to write it like that. You're probably going to want to write it like this eventually because things will get really complicated and you don't want to write them out twice. It's just super cumbersome. So totally fine to write it with this shorthand notation. Just be clear that it is two things. It's x is I root 2 or x is negative I root 2. So there is two ways to make this true. And you should plug them both back in and test them. Test one, see if it makes it true. Test the other, see if it makes it true. Really prove to yourself that there is two answers. All right, great. Well, I'm just going to call that there. We'll pick up next time on that.